Hola, buenos días. Me llamo Jessica Grovesmith, trabajo en el Passive House Institute en Alemania, en Darmstadt, y estoy muy feliz ser parte de esa conferencia de PEP y hablar sobre el tópico de eficiencia para piscinas. Guidelines for Passive House Indoor Swimming Pools. Swimming pools are very energy intensive. They need a lot of heating energy and also electricity to be able to provide the warm air temperatures, but also the warm and clean water for people to swim in. We have high temperatures of around 30 degrees for the air within the swimming pool. The water is typically around 28 degrees. We also have need for dehumidification from the evaporation from the pools, and we have to provide the technology to keep the water clean. All that energy input also means that there's quite a lot of potential for energy savings. So thinking through how do the energy needs actually, where do they come from? Thinking those through and reducing those energy needs is what we want to achieve. So to tap into those high potentials for savings, to reduce not only the energy needs, and with that also reduce our our emissions, and our running costs. So the idea is to apply the passive house concept to pools. We want to provide comfortable and healthy conditions within the building with the lowest possible energy input. That is the passive house idea and the concept. We look at the combination of optimizing the thermal envelope as well as the mechanical systems and how to operate the building. What does that specifically mean for pools? The numeric criteria of a normal passive house in terms of 15 kilowatt hours for heating don't work for a pool because they are so much more energy intensive. So it's been an applied research topic at the Passive House Institute for over 10 years, since 2009, where we looked in detail what the energy saving potentials for pools actually is. So starting off in 2009, we did a feasibility study, a research report, and we worked very closely with a design team who were building a new public swimming pool in Lünen, which is a town here in Germany. We worked very closely with that design team and the municipality to exploit the potentials, and which eventually led to the opening of not only one, but two pilot projects in Germany. On the left-hand side, the Lippebad in Lünen. On the right-hand side, you see a picture of the Bambados in Bamberg in southern Germany. Both of these projects opened their doors in 2011 as pilot passive house swimming pools, and we were very lucky and fortunate that we were able to secure funding to actually monitor those projects for 2 whole years to check the performance and to see whether the research that we had done in advance really worked and whether we were achieving those energy savings that we had predicted. There are many, many learnings from these projects that I will share with you as part of this presentation. The main thing that people are interested in initially is how high are these energy savings? What are we talking about when we apply the passive house concept to pools? So what you see on this graph is the outcome for these 2 pilot projects in terms of the energy savings for both heating and for electricity. On the left-hand side are the savings for the Lippebad, on the right-hand side for the Bambados. Now, it's difficult to compare because all of these projects have slightly different uses, different temperatures, and different facilities. But we compared for the specific project, we compared them with projects of a similar size and similar facilities. And what you can see are the bars in red, that for heating, we in both projects achieved savings of around 60%. And for electricity, which are the bars in yellow, we have savings between 20 and 45%. So those are quite substantial numbers. And keeping in mind that these are pilot projects, this is the first time this has been implemented to that scale. We know there is further potential for even further savings. So having kind of that proof and evidence and seen that the concepts that we developed worked in practice, we worked more with these projects and we started consulting on new projects as well. So our research has been ongoing ever since, and we've been consulting on projects worldwide. The 2 most significant ones are listed here in this slide. There's St. Sidwell's Point, which is a leisure centre currently under construction in Exeter, in England, which should open its doors in next year, in 2021. And then we also provided some consultancy for a project with a swimming pool in China, in Qingdao, which has different challenges because that's a different climate. So we've been learning and applying our research in new projects. Also in Spain, there's a hotel in San Sebastián which has a pool involved, where we also applied and consulted with some of our ideas. Now, we've gained all this knowledge and we apply it when we consult new projects, but we wanted to make sure that this kind of information gets available for new clients and for design teams. So we were able to publish a concise guideline booklet, which clients and design teams can refer to get insight into the recommendations for energy efficiency measures for such projects. And these guidelines are published on our website. It's a PDF document which is available in both German and in English. The link is here included on the screen, where we summarized all our findings from our research into the main guidelines for energy efficiency measures for indoor swimming pools. And that covers recommendations for the thermal envelope and kind of zoning within the building. It covers recommendations for the ventilation strategy, energy efficiency for the pool water treatment, for the hot water system. We also looked at cost analysis for specific components, and we gave some guidelines for commissioning and operation. And it's the essence of these guidelines that I want to talk through within this presentation. There's a lot to say. I could do a whole day's workshop on this, but I want to give you some insight and at least talk you through kind of the main insight as part of this presentation. So starting off, as with any energy efficient construction, it's best if you think this through from the very beginning. It's a lot easier, a lot more efficient, a lot more cost effective if you embrace the idea of energy efficiency from the very beginning when you set out the design of your project. So within these leisure centers, within these swimming pools, we always have areas of different temperature needs. We have the pool hall, which is at around 30 degrees. We have the changing rooms and showers, which are at 26 or 28 degrees. And then we have offices and we have the entrance area, which is typically at 20 degrees. So we need to condition those spaces separately. And it helps immensely if during your initial design, you make sure that those different temperature zones are separated and in the layout. That's something to keep in mind from the very beginning. As part of the whole energy efficiency process, we work with the PHPP, as in any passive house project, to do our energy modeling and our optimization procedures. Because we have these different temperature zones and different comfort conditions, we have to work with multiple PHPPs in this case, so multiple zones with different temperature conditions. In the research projects, we had a specific multi-zone PHPP. We are working at the moment in the new projects to integrate multiple zones in individuals' PHPPs. And if you're interested, I'm happy to reach out to me afterwards and I'm happy to discuss further. So we work with a normal PHPP, as I said, with separate PHPPs for the different temperature zones. Now, because these pools have additional facilities, we have over the time developed some additional calculation tools. Oh, let me go back one. Yeah, so there are some supplementary calculations that we need for these pool projects to be able to allow for the energy impact of evaporation from the pool surface, for example, the energy balance of the pool water, but also the additional electricity demand that we have for the pool water treatment. And that's a pool that we've developed at the Passive House Institute. We call it the pool tool, which is under development and that we use as part of the consultancy process for new projects. So talking generally about applying the passive house concept for these kind of projects, for passive house pools, we have our 5 pillars of passive house: insulation, airtightness, good windows and thermal bridges, as well as ventilation with heat recovery. We apply the same concept, the same ideas for the pool hall, and that immediately already leads us to reduced space heating demand. The passive house envelope brings us a long way in these projects because we have such high interior temperatures. So a good thermal envelope brings you a lot of savings. That's the first step. That's the entry door to our energy savings. Now, interestingly, if you think about that even further, this opens many more doors, which we try to exploit to its full potential. So the idea is, by having this very high quality thermal envelope, of passive houses with a good insulation, no thermal bridges, we have high surface temperatures, which gives us much more flexibility in terms of our ventilation strategy and in terms of reducing evaporation losses and humidity concerns. So some of those aspects I want to go into in a little bit more detail. One topic is the recirculation of air. So in pool projects, we have a high amount of ventilation that we need to provide to the pool halls constantly. There are two reasons for this. One is for air quality. We need to provide fresh air at all times. We need to make sure we remove any chemical contaminants within the air from the usually chlorinated water. The second need for fresh air is dehumidification. So we have a lot of evaporation from the pool water surface, and that humidity needs to get taken out of the pool air. And that is typically done in our climate conditions. That is typically done by controlling the airflow rate. So what you can see in this graph is that in blue we have our outside airflow rate, which is driven by the need for dehumidification. So that's fairly constant and low in winter when it's dry outside. In summer, we have a higher need for outside ventilation because the humidity level outside is higher. And this is measured data from the Lippebad here in Germany. Now, typically, conventionally, the operation strategy is for the ventilation systems that they run at 100%. So everything that you see here in green in the background is run as recirculation air. And the main reason for that is that we constantly, in traditional buildings, you constantly provide dry and a lot of air to the windows, to the surfaces, the outside surfaces, to keep them dry. We don't need that anymore in a passive house because we have the high quality thermal envelope, so we don't need that recirculation anymore. And if we take away that recirculation, electricity demand to run the ventilation drops down significantly. This is what you can see in this graph. This is monitored data over 2.5 years from the Bambados project. On the left-hand side, you see the ventilation, which is running pretty much conventionally with a lot of recirculation air. Towards the right-hand side, we managed to optimize the strategies and take out that ventilation, the recirculation, which led us to significant electricity savings of around 60%. Now, that's not only energy savings, but that is substantial monetary savings as well. So that is one door that the passive house concept opens, and that is fundamental for the passive house concept for pools. We leave out the recirculation air and work only with fresh supply air needed to provide good air quality and sufficient dehumidification. Now, there's a second aspect. Because we have such a good thermal envelope, we are much more flexible in terms of the distribution of the air. We don't have to blow dry, hot air onto the facade. We are much more flexible. So the idea is, and we spent quite a lot of time modeling this and experimenting also in the pilot projects in terms of how we can optimize the air distribution. And the recommendation is the best, or a recommendation for high energy efficiency and high air quality, is that you extract the air at the bottom of the pool, so very close to the pool surface. That gives us good conditions because it provides a layered kind of strategy for the humidity. It also gives us good air quality because all of the contaminants from the water get extracted immediately at the source. The benefit of this is that the humidity stays low towards the bottom of the pool, which is a comfort aspect, but also an energy efficiency aspect, because high humidity at the pool surface provides us energy savings again. And I want to explain that in a little bit more detail. This comes to the topic of evaporation. Evaporation comes with energy losses. It's an energy intensive process. And it's driven mainly by the pressure difference between the air and the water. So we can influence the evaporation depending on our set points of the humidity in the air. Lowering evaporation has benefits because it means we have less needs for dehumidification, which leads to lower electricity and heating needs. It also means that we have less evaporative heat losses from the water, which means we reduce our heating demand for the pool water itself. So trying to keep that evaporation as low as possible is a big strategy in terms of energy savings, and we can do that, as I said earlier, by modifying the set point, the humidity set point of the air. The higher the relative humidity of the pool hall air, the lower your evaporation. We experimented with that in the actual build projects. What you can see here is a series of experiments. In the top graph, you see the humidity level that we set within the project. So starting off with 43%, which is a typical humidity level that pools are conventionally operated at. And then we increased that step by step to see what the impact would be on the energy consumption. And looking at the data carefully, we could see immediately that, yes, the evaporation goes down, the dehumidification goes down, and the data also shows that the heating consumption for the pool water decreased. So this has confirmed the idea or the notion that higher humidity levels help us to reduce the energy needs. So the recommendation for passive house swimming pools is to operate at a set point during the daytime of 55 to 60% relative humidity. And we can do that in a passive house pool because we have such a high quality thermal envelope and there is no risk of condensation at the surfaces. So what I want to show you next is a typical energy balance of a passive house swimming pool. This is actually the monitored data from the Bambados project. In the red and orange colors on the left-hand side, we have the energy consumption for heating. On the right-hand side, we have the energy consumption for electricity. And you can see that there are different factors that play into this. The dark red is the space heating. So this is mainly the heating for the pool hall. Then there's a big portion of heating also for the pool water. There's some heating needs for the showers and other warm water, and then there's a substantial amount of electricity for all the technical equipment, for the pool water treatment, the ventilation, and so on. And I want to go into all of these in a little bit of detail and mention the main saving strategies. So talking about the pool water, in both of our projects that made up about a little bit more than 40% of the overall heating energy, so that's a substantial part that we want to understand better and make most of the energy saving potentials. What we did as part of our research work is to set up a fairly detailed energy balance calculation for the pool water. So looking at where are the heat gains and where are the heat losses for the actual swimming pool. Looking at the main influencing factors, which are shown in this graph here. So we have several heat gains from the people and the pumps, possibly also solar gains, but we also have substantial losses from the evaporation, but also from the continuous amount of fresh water. We looked at all of these in detail and we set up a tool for this kind of energy modeling for pools. Without going into too much detail, I do want to point out the main influencing factors and the main aspects that you should keep in mind to lower the energy demand for pool water heating. So the most obvious is obviously the temperature set point. The colder the water temperature, the lower the energy demand. That's typically a given by the client and by the needs of the temperature, but you do have an influence on that. So typically it's about 30 degrees for a non-swimmer's pool, it's 28 or 26 degrees for a swimmer's sports facility, but the lower you can keep it while still providing the comfort for your customers, that's the main aspect for reducing the energy needs. Now the second large influencing factor is the rate of evaporation. The more evaporation, the higher your energy needs. So any measures that you have to reduce the evaporation, the better. And one of the very effective means, as I mentioned earlier, is to increase the set point of your air humidity. And third, very influencing factor is the amount of fresh water dilution. Now, obviously, we have to provide a certain amount of fresh water per person for hygienic reasons. Depending on the choice of filtration system, on the filter technology, there are higher or lower rates of kind of fresh water needs that pools typically have. This is something to look at in detail during the design of your process. The passive house concept does not prescribe a certain filter technology. It's open to different ones, but you do have to make sure that the overall energy efficiency targets or recommendations are met. If you choose a system that actually has high amounts of water needs, then there are possibilities to reduce the energy demand by using technologies of wastewater heat recovery, for example, which we did in the Lunan project, and which was very, very effective to regain some of the heat from the wastewater. So another topic I want to talk about is the electricity needs for the actual water treatment to provide the clean water. There are several aspects that go into this. We need to provide sufficient water distribution, filtration, and disinfection. The important role for you as a designer to be aware of all components and to exploit all the saving potentials in terms of how you operate those pumps and how many pumps you actually need. There are many details to this. The topic that I want to talk about, which is the most important, is the electricity demand of the circulation pumps. So those pumps that actually circulate the water 24 hours. They are the ones that need substantial amount of electricity for the pool projects. And it's an absolutely important design task for you to reduce the pressure losses when you design the system. It's also important to select efficient pumps themselves, and then there are ideas that you can actually play around with the operation and use lower circulation rates at times where there are less bathers in the pool. For this part of the project, because it is so energy intensive, we actually developed energy targets. So you want to be aiming for 24 to 40 watt hours, 24 to 40 watts per cubic meter per hour of circulated of water. So what you see in this graph is an example of how you can reduce the pressure head throughout the system. Our recommendation is to aim for 5 to 10 meters pressure head. So this is a crucial design task for you to keep in mind. And you can find details about this in the actual published guidelines. Now we're running a little bit out of time, but I do want to mention the last topics. So domestic hot water, the actual heating needs to provide the shower water. Here it's important to make sure you work with low flow shower heads, so a maximum of 6 liters per minute. Choose a good product, but there are many and increasingly more available on the market. This is certainly something that requires no or very little extra investment and comes with energy and cost savings. For the heating demand for hot water, there's also the possibility to work with heat recovery systems. We have not tested these systems yet in our pilot projects, but they look very promising, and I'd be very interested and very happy to do so in future projects. We're becoming increasingly familiar with them in residential projects, and there have been other projects in pools where these can be applied. So that has a lot of potential. Now, there's a lot of extra consumers with high electricity needs in such projects, depending on the facilities. Lighting typically has a high electricity demand, as does the electricity to run the ventilation throughout the entire project. And there's a big part here that is just entitled as other, that includes all the additional kind of equipment that you have in these complex projects, but also often there are additional spa facilities or kitchen facilities. So you need to understand all the facilities within your project and try to keep the energy and electricity demand as low as possible for all of these aspects. So having an overall energy balance is important. For efficient ventilation, it's the same concept as we are familiar with passive house. So we are looking out for high energy efficiency recovery rates and also low as possible electrical efficiency rates. What's important to keep in mind here is that you take a very close look at appropriate sizing and also controls for the ventilation system. In pool halls and in kind of the shower areas, ventilation systems are usually dimensioned quite generously because we need high ventilation rates in summer for dehumidification when there's high occupancy also, but there are times where there are less people and where it's drier outside. So there's a lot of potential to actually run the ventilation systems at lower rates. So work with temperature sensors, humidity sensors, CO2 sensors, as to keep your actual flow rates low and your efficiency high. Now, there are many other facilities. You need to look at the lighting, the overall electricity efficiency for your controls, look at your water features, any additional facilities you might have, and go through details. We don't have time to talk about all these details today. We have some general recommendations within the guidelines that you can take a look at, and I'm happy to discuss afterwards in detail if you're more interested. It needs to be a holistic approach. We do an energy balance for the entire project, including the heating and cooling system, to achieve overall energy efficiency within the line of the kind of passive house concept. Now, these projects get quite complex, so the last topic that I want to talk about is the topic of commissioning and in-use optimization. With our pilot projects, we will only achieve these substantial savings because we made sure after the projects were actually commissioned and in use, we made sure we spent quite some time with the operators to look at whether the project was actually being operated the way that we had envisioned. And these substantial savings that you see here, for the example of the ventilation, we only managed to exploit those because we worked with the operator step by step to make sure the building was being used as planned. Because this is such an important topic, our guidelines also include some templates, some recommendations for energy management as part of the commissioning process, but also once the project is in use to help you keep track of your actual energy performance. And again, these templates are available for free for download on our website, and you can see the link here. So I hope I've been able to give you a rough oversight of the main kind of energy efficiency strategies. The question is, what's next? If you're interested in learning more, and there are a lot of technical details to dive into here, I suggest, first of all, you go online, you actually download these guidelines and checklists and have a look and see how those apply to those projects. The full research reports for the pilot project are available only in German, unfortunately. Some of you might be able to read German. There are summaries of the main points available on Passopedia, and I've included all links here on the slide. What's next? If you're actually interested in pursuing this further in your projects, then please do reach out, get in touch. I'm more than happy to share more experiences, and I'd be very happy to see more and more of these concepts applied and have more passive house pools being planned and being built in Spain and also in other parts of the world. And with that, thank you very much, and I look forward to hearing from you.